Okay, let us start then. Good morning, everybody. I will try to do two more things in this discussion of grand canonical ensemble. One is having to do with the real meaning of chemical potential. It is phase equilibrium. Let us imagine that we have a box, a cylinder, initially having two faces. Consider two faces of the same material, if you like. Let's consider vapor phase, let me call it phase A, and a liquid phase, phase B. I will try to get a condition for their coexistence together. Coexistence means phase boundaries. If you look at the phase diagram, you see that two phases may be separated by a curve. So what is the condition having a phase equilibrium on that curve? Okay? And for a specific example, I took vapor and liquid coexisting together. Now, the condition, the phase boundaries are determined by the Gibbs free energy and the Gibbs free energy by definition is U minus Ts plus PV, or Helmholtz free energy plus PV. And we also know that it is chemical potential times the number of particles, because chemical potential is nothing but the Gibbs free energy per particle. So you can also write this as mu times total number of particles. Well, particles in the sense could be atoms or molecules making up the specific system you have. So let's look at the total number of molecules in your system then is nothing but the sum of those in one phase plus the sum of the other thing in the other phase. Number of particles in phase B. And Gibbs free energy then can be written as Gibbs free energy of the part in phase 1 and the part in phase B you can write these, right? Rather easily for this two-phase system. Now, if they don't coexist together, then there will be particle exchange from one phase to another. And as the numbers will be changing, that means Na and Nb, G changes, Gibbs free energy changes as follows. As the numbers are changing, this is the change in the number in phase A, and here is the same for phase B. Well, If the number of particles are changing, dNA will be minus dNB, isn't it? It will go from one phase to another. As one is decreasing, the other one will be increasing. So, minus dNA is dNB, for example. Using this, you can rewrite dG as mu A minus mu B dNA. Isn't it? And at equilibrium, this Gibbs free energy will be minimized. So let's write that condition. So dG will be smaller than or equal to 0. Okay? So that gives us a condition depending on mu A or mu B, which one is bigger. If mu A is bigger than mu B, of course, NB will increase. And A will decrease. The reason is the particle exchange will be from higher chemical potential to lower chemical potential, isn't it? So let's look at in the opposite case, the opposite will happen. If mu B is bigger than mu A, then MB will decrease and A will increase. The particle transfer will be in the other direction. Obvious. Now, let's consider the equilibrium case, analyze the equilibrium, where no more particle exchange will happen. No more particle exchange means chemical potentials will be the same. So, coexistence means between two phases means exactly chemical potentials are equal. Now, let's look at this in PVT systems, pressure, volume, temperature, and look at the coexistence pressure. Okay? If you define it to be P sigma as a function of temperature, you know, you can always get a cross section at constant volume and write the phase diagram as PT diagram. Let's look at the condition this pressure should satisfy, coexistence pressure. It will, of course, satisfy that condition What was the condition for equilibrium? Chemical potentials should be the same. Pressure and temperature should be the same. Otherwise, heat transfer will be happening. So at equilibrium, you have to have these already established. Now, let's look at the derivatives. If these are equal, derivatives will be related, and the relation is, let's take derivative with respect to temperature. Only depends on temperature. Okay? In one phase, that's the thing. In the other phase, it's very similar expression. So that's what we get from the equilibrium condition. So if we define quantities per particle, entropy per particle, and specific volume per particle, we can rewrite this as follows: dp dt, rate of change of this equilibrium or the coexistence pressure with respect to temperature, is SB minus SA, VB minus VA, in terms of these quantities per particle. These are small, say SPSA, or delta S, delta V, or L over T delta V. Now, of course, these entropies are coming from the fact that these are minus d mu dt at constant pressure, and V is d mu dP at constant temperature. We have used this or shown this before. The equation, the last equation, is the Clausius-Clapeyron equation. And I have defined one more quantity, L, which is the latent heat. To change the substance from one phase to another. So L is nothing but T delta S. T times delta S is heat flow. If there's no phase transition, this heat flow will change the temperature of the system. But at the phase transition, it will change some part of the material into the other phase. If you take liquid, for example, give heat, it will go into vapor. Okay? I will give this when I consider interactions between particles as an example of phase transition. Again, I will do this as an example of a type of phase transition. So the equation, Clausius-Clapeyron equation, is this equation. Now you probably remember this. Or just that equation to be specific. Relating coexistence pressure to latent heat per particle. This is because all the other quantities in it are defined per particle. Did you remember it now? Probably still no. Extremely useful. Well, I am trying to prepare you for the interactions part and also phase transitions, which is going to be an important part of this course for the interacting particles. But of course, before that, we have to study the quantum gases. We have done the classical one, but quantum gases are still to be done. Fermionic gases and bosonic gases. Okay, that's one before the last topics in this grand canonical ensemble. What was happening is that there is energy exchange and particle exchange. So this means there must be fluctuations in energy and in number of particles. What are these fluctuations? That's the last question we are going to answer. Of course, in canonical, there was only exchange of energy between your system and the heat reservoir, so only energy can fluctuate. Number of particles were fixed. So here, both number of particles and energy fluctuates. Let's find those fluctuations. This is the last thing I will do in this subject. Why don't you ask the person who is responsible to do problems to something with this? Okay? Clausius-Clapeyron equation. Now, let's start with number fluctuations in grand canonical ensemble. Of course, by definition, we know that the fluctuation square is related to average of n squared minus average n squared. And when you look at the average number of particles in your system, you can also use the other notation. This is nothing but multiplication of the number of particles in a specific state with the probability of your system to be in that state, minus alpha n r minus beta ES. and the normalization factor, which is the grand canonical partition function. Yeah? We have to multiply the probability with the quantity whose average you are taking. If this is the average, then let's check the derivative of this average with respect to alpha. Keeping temperature and energy is constant. Why do you want to consider derivative with respect to alpha? Because it will bring down NR, isn't it? To have a contact with this relationship. If I want to find the averages with respect to averages of energy, then I have to take derivative with respect to beta, isn't it? To bring down energy. So that's why I'm considering derivative with respect to alpha. So if you do that, well, you can consider this as multiplication of two terms. The first one is this. The second one is 1 over the quantity. Very easy derivative to take. It is minus, well, derivative with respect to alpha brings down an NR. You have NR squared negative into the minus alpha and R minus beta ES times the 1 over the partition function plus this first term times the derivative of 1 over the quantity. Well, that brings down an NR if you take derivative with respect to alpha. Since 1 over the quantity, derivative of first is 0, derivative of first times the denominator, isn't it? You know the rule, obvious. The exponential term times the same thing, the first times the derivative of second, NR e to the minus alpha NR minus beta ES square of the quantity in the denominator. Isn't it? So the first term, as you can see, is related to average of n squared. The second term is square of the average, isn't it? So this is nothing but minus average n squared, that is plus n average squared. So this derivative, negative of that derivative is exactly the quantity we are looking for. So delta n squared average, which is n squared minus n average squared, must be equal to minus del n bar del alpha beta yes. Not very difficult to get that. Well, you can look at the definition. We are writing the first term as plus alpha term, isn't it? The relation gives us del mu del alpha as minus kBt. Del mu del alpha is minus 1 over beta. Beta is itself 1 over kBt. It is minus kBt. So, we can write the following: minus del mu del alpha, del n bar del mu Tv. What is this? It is minus del n bar del alpha, chain rule, is nothing but plus kBt del n bar del mu, keeping T and V constant. So let's use this to get delta n squared average, or delta n squared average is kBt del n bar del mu, keeping T and V constant. That's where we are. Now let's consider again quantities per particle. This is N over V, number of particles per unit volume, density, if you like, number density, and let's look at relative mean square fluctuation. That means delta n square average, not the total, but the particle per volume, per unit volume, with n bar squared. This is the relative fluctuation. That is going to be exactly equal to our total number of particles squared average, average square, isn't it? Volume will cancel. And that will be again equal to kBt over n bar squared del n bar del mu T and V. Now we have to see the meaning of that derivative. It must be related to a response function. Let's discover that response function. Again, volume per particle, defining quantities per particle, and that gives us the same thing, isn't it? N times small v is v, volume per particle, times the number of particles is the total volume. So using this, we can get average delta n squared divided by average n squared is kBt divided by v small v squared delta v small v del mu Tv. You can simplify this by writing v squared divided by capitals v squared volume per particle divided by the total volume squared kVt del v del mu at Tv. To get to that response function, we have to see what dV d mu is using the following. Well, I'm really doing something very similar what I did for the canonical ensemble for energy fluctuation. Very similar calculation. Let's recall that d mu is v dp minus s dt, or at constant temperatures it is v dp for constant temperature dt is 0. So this means derivative with respect to mu can be written as related to derivative with respect to pressures in this form. And of course, this derivative is 1 over small v derivative with respect to p. That will give us the response function we are looking for. So let's write delta n squared average and average squared as minus kBt. Let's take this negative side inside the quantity minus 1 over v, then v, then p at constant temperature. What is the quantity inside the parentheses? It's a measure of what? Let's look at it from a physical point of view. This is percentage change of volume, isn't it? Delta V divided by V is percentage change in volume when you apply pressure. So how much the volume changes when you apply pressure, isn't it? Percentage change in volume when you apply pressure. What is that? It must be a response function that can be measured experimentally, isn't it? Apply the pressure and see how much is the volume changing. Do you know what that is? It is compressibility of the system. Compressibility. How easy or difficult to change the volume when you apply pressure. since it is at constant temperature, it is isothermal compressibility. Compressibility. So this quantity, relative fluctuations, is related to kVt over volume times the isothermal compressibility, kappa T. Is it kind of similar to what we have found for energy fluctuations in canonical ensemble? We also found these fluctuations responsible to a response function. Do you remember what was it for canonical ensemble? We found it to be proportional to the heat capacity, isn't it? Well, these results are quite important, specific examples of what we know as fluctuation dissipation theorem. I don't know how you are listening to this, but you should always think in terms of physics, physical interpretation of things. We are not doing calculus only, taking derivatives of whatever, but the result is quite meaningful, this result. Now let me calculate this for a specific system, and the system we all know is the ideal gas. Let's see what is this for an ideal gas, okay? At least we have a feeling of how this should be related to the number of particles. Is it a large quantity, a small quantity? We should have a feeling for this. We expect this to be small, isn't it? Unless we are near a phase transition where these fluctuations can become large, but away from the phase transition it must be small, and we should see that it is small by doing this specific example for a classical gas. Okay, let's take a classical gas and calculate this to see how big are these number fluctuations. We should remember that because, well, if you don't have a feeling for the numbers, we forget it. That's what's happening to you in your undergraduate education. Let's take the example of an ideal gas. For an ideal gas, we can write the following. The average number of particles is, remember, I have found this. Is related to logarithm of the partition, grand canonical ensemble partition function. So if we know the partition function, logarithm of it, I think you should remember the specific result. Check it. So the result will be, since you are multiplying again with z, zv lambda t cube, which is nothing but ln of grand canonical partition function. We also know the average number of particles for a classical gas. in terms of PV, kBT. We have proved that one too, that classical gas obeys that equation of state, thermodynamic state, so that PV is N bar kBT. So let's calculate del N del mu chain rule. Well, we have the result at our hand, so we can calculate these. That comes out to be beta e to the beta mu times v over lambda t cube, or beta times the average number of particles. So it is PV over kBT cube. On the other hand, del P del mu can be calculated as 1 over V del N del mu which is P over kBT squared. So delta N average squared can be related to kBT, delta N average del mu PV over kBT, or N bar in this case, because it is changing. So at the end, we get the following. Delta N is related to square root M bar, so that delta N over N bar is nothing but 1 over the square root N bar. So that's what you have to remember. If total number of particles is huge, in a gram of copper, 10 to the 23, that says fluctuations are very small indeed, isn't it? It goes like, relative fluctuations goes like 1 over square root the number of particles, very small. So that's why we replace N bar by N, isn't it? Because the fluctuations are so small, you can always do that. Do we have any questions about this? Now, do you remember what we found? Relative fluctuations are proportional to the compressibility of the system. Number of particles are fluctuating because your system is exchanging particles with the particle reservoir. One last thing, we are going to have also fluctuations in energy in the system, as in the canonical, because there's energy exchange with the energy reservoir. So the reservoir with which your system is interacting is a particle and energy reservoir. They are changing. So if the number is changing, at equilibrium, of course, these changes will slow down and become very small. That's why we can identify averages with the actual number of particles and actual energy. I will do the energy in the next lecture after the break, and that will finish the chapter number 4. Thank you.